Okay, so getting into 4.2, talking about the basis for what we call the derivative in calculus. Starting to get into really some of the good stuff with calculus, the basis for everything we're going to talk about in this chapter, building off of what we talked about in 4.1 with limits. What we're really going to start with is the concept of rates of change, which is all we're talking about when we talk about the derivative. All the derivative is a measure of the rate of change, and what we're familiar with is the average rate of change. Average rate of change. And that's just our change in y with respect to the change in x, which we've seen before. This is one of the ways we talk about slope. I'm going to reword that way we talk about slope. So instead of thinking about it just as y2 minus y1 over x2 minus x1, I'm just going to use some different notation here. And instead of talking about y2, we're going to talk about the function value at x2, so f of x2 and f of x1. That's our average rate of change. We know it better as the slope, or the fancy IB word for that is gradient. So if you see gradient at all in a problem, all we're talking about there is slope. So kind of getting off on, no pun intended, because we're going to talk about it in a minute, but getting off on a tangent, secants and tangents. A secant is a line that just intersects a curve at any point. So if I have my graph as I do over here, maybe my secant line looks something like this. Right, here's my secant line. And I can concern myself with 2 points on that curve. All right, let me actually zoom in a little bit here. 2 points on that curve that I'm concerned with here, and that would be x1 and x2. Right, and if I wanted to know the slope of this secant line, well, this is just the average rate of change, right? I want f of x2 minus f of x1 divided by x2 minus x1. So the slope of my secant line here is just my average rate of change. So maybe I'll just move that over here as well. The slope of the secant line, we'll use, this is kind of my notation here, but just so I know that I'm talking about the secant line, that's just f of x2 minus f of x1 divided by x2 minus x1, just like the average rate of change formula that we talked about. Well, instead, I'm going to just change this a little bit. If instead I talk about an x1 and an x2, I talk about an x, and then I talk about a point h units away. So instead of x2, I really have x plus some h units that I've moved. Well, now what's the slope? Well, the slope of our secant line now would be f of x plus h minus f of x over, well, it would be x plus h minus x, which is just h. This is the way that we're going to start to formally define the secant line, because it's going to connect with our the way we're going to define tangent lines. So a tangent is a line that touches the curve at a single point. So there's my key here, just a single point. So maybe my tangent line will look, zoom in here so I have some room. If I'm concerned about the tangent line at this point, let's see if I can do this. Try that one more time. Right there, right? And I can see that it only touches at that one point. The question we want to know, the question we're going to ask ourselves to get from secant to tangent is, what happens as this h that we have, this distance between my 2 points, approaches 0? What happens as this distance decreases? Well, the simple answer, of course, is that the points move closer together. Well, then, what does that mean? Well, let's take a look at it. So if I find my secant line graph here, I've got 2 points. You can see my 2 points in purple here. And if I play around with this distance between the points, I want to know, I set this all the way up to 3 first, what happens as the points move closer together? You can see it start to move closer and closer and closer together until they wind up right on top of each other, and they effectively touch the curve, touch the graph at 1 point. That's going to set up our tangent line. So what happened? Well, let's show that one more time. I have 2 points here. And I'm going to move those points closer together, right? The distance between them, my h, my distance, approaches 0, and my points get closer together. So I'm starting with a secant line. And we know that my slope of a secant line is just given by our normal slope formula. But this h is decreasing. This h is approaching 0. So what happens? Well, we can redefine our secant formula and repurpose it for tangent. So the slope of the tangent line is given for one specific point, and we can calculate that. I'll use m tan just to set it apart, as the limit as h approaches 0. So here's my limits again of what just looks like the secant line slope formula. F of x plus h, write that better, f of x plus h minus f of x divided by h. So this is the slope of the tangent line, right? Talking about what happens as my points for the secant line approach each other. This is also known as instantaneous rate of change. Instantaneous rate of change. At that specific point, right, at our specific point right here. What is the slope of the line at that point? Roughly, we can only approximate it so much because we only have one line, but that's what the limit's for, right? It looks like it's going to be this. I don't care what it really is. It looks like this is what the slope is going to be, so that's what we'll call it. So for example, I can use this and I want to find the slope, or again, IB calls it the gradient, of the curve y equals x squared at the point negative 2, 4. So I have to give you a point to use here because it's an instantaneous rate of change. So we can do this. I give you 1 point, right? You have 1 point. This is an instantaneous rate of change, which means I want to use my slope of the tangent line. So the limit as h approaches 0, we'll just write it out in general first. So f of x plus h minus f of x divided by h. Let's substitute in. Work a little horizontally here just so I have some space. This would be x plus h squared minus x squared divided by h. So I have x squared plus 2xh plus h squared minus x squared. That's going to carry over. So those cancel out. I can also factor out an h in the top, right? So these cancel out. And then I have an h in common here. So my goal with the slope of the tangent line is to find some way to get rid of this. right? We need to eliminate this denominator if we can, especially here, because if I plug in 0, I'm going to be dividing by 0, and I can't do that. Which is what factoring out our h helps us do. Cancellation. I realize I haven't been carrying over the limits, but that does still apply. So the limit as h approaches 0 of 2x plus h. Actually, let me go back in and add those in just to stay consistent. It's always important. So let me go ahead and just paste this a few times. So just to recap as I'm finishing this up, one of the things we want to do with limits is to try to simplify this as much as we can. Once we've simplified it as much as we can, right, this step right here is pretty fully simplified, then I can just go ahead and plug in 0. So at any point x, the slope of the line tangent to this curve is going to be 2x. But I care about a specific point, right? So the slope of my tangent line is 2x. But how about at the point negative 2, 4? Well, I'm looking at when x is negative 2, so I'm going to go ahead and substitute that in, and I get a slope of negative 4 at that point. So starting with our limit definition of the slope here, expanding that, simplifying it, and using it to find the instantaneous rate of change at that specific point. So similar idea, but thinking about it maybe a little bit backwards here, is to find the point on the graph of 1 over x where the gradient is negative 1 over 4. So no matter what I'm doing throughout, my goal ultimately is for the slope of the tangent line to be equal to negative 1 over 4. Right, I'm talking about a specific point, so I know I'm dealing with a tangent to the graph. Let's figure this out. I'm dealing with the slope of the tangent line, which tells me I should maybe use that formula. So the limit as h approaches 0 of f of x plus h minus f of x, and it's all divided by h. Start substituting. I'm not going to forget to carry my limits this time, so I have 1 over x plus h minus 1 over x, and that's all divided by h. It's a little cumbersome looking, but let's take this a piece at a time. So we'll start with our numerator, and I can just make a common denominator here. So I'm going to have x minus x plus h over x times x plus h, still all divided by h. I'm going to simplify that, so that's going to be negative h on the top. All right, so I have negative h over, maybe I'll distribute here as well, over h. If I were to finish off this fraction, I'd get negative 1 over x squared plus hx. This is as simplified as I can make it right now. So I can go ahead and plug in my h equals 0. Right, so I can go ahead and use this now. So I get negative 1 over x squared. This is kind of my general formula for the slope of a line tangent to this graph at any given x value. Well, I want to know what x values I need to get a tangent, or my tangent line to have a slope of negative 1 over 4. So we've said that the slope of the tangent line is negative 1 over x squared. I also know that that needs to be equal to negative 1 over 4. Well, this of course means that x squared has to be equal to 4. And so x can either be plus or minus 2. All right, so we're still applying this tangent formula, but we're doing it with a little bit of extra information in mind. So this way I have some other information at my disposal that I can use to help myself solve the problem, which is a great IB skill, right? Using prior knowledge, using other knowledge, not just simply plugging into the formula, but applying the formula and using it to solve problems, right? Really, really good quantitative reasoning, problem-solving skills. So this brings us right up to the derivative, which is one of kind of the cornerstones of calculus. So the limit definition of the derivative is something you've already seen. It's just the equation for the instantaneous rate of change. It's important to know, it's important to start associating right away that the derivative is just a calculus word for slope. All the derivative does is tell us the slope of the graph at that specific instant in time on the graph. Derivative is slope, always. Keep that association fresh in your mind. Okay, well then, we'll say that the derivative of f, with respect to x, almost started abbreviating, with respect to x is, and we have this f prime of x notation. And that's going to be equal to exactly the instantaneous rate of change formula. Limit as h approaches 0 of f of x plus h minus f of x, all divided by h. So I brought this up, right? So we said this can be read as f prime. Now that's one of our notations that we have for the derivative. Right, so we have this f prime of x, or we have this dy by dx notation. We'll use both interchangeably. One is better in some contexts and the other is better in others. We won't talk about it right now, but you'll kind of see along the way. One works better in one context, one works better in the other. What's great about this one is it looks like the slope formula. It looks a lot like delta y by delta x, which is great because it helps us really firm up this connection between the derivative and the slope, which I think is really helpful. So you will see both throughout. By the way, too, if you ever hear or see finding the derivative from first principles, that's also what this means. If I were to say find the derivative of the function from first principles, you know that that just means use the limit definition of the derivative. So let's try a couple. If f of x equals x squared, find f prime of x. Find the derivative. Well, we don't know any tricks yet. We don't know any shortcuts yet, but we will soon. So for now, we're just going to apply the limit definition of the derivative. Actually, we've done this work a little bit already, right? So x plus h squared minus x squared over h, which we said was going to be x squared plus 2xh plus h squared minus x squared. I'm forgetting the limits again, so let me add that back in. Add this back in real quick. And we can cancel out those x squareds. We can factor out an h. So I'm going to get h times 2x plus h. My h's cancel out. And of course, this is simplified as fully as I can, so I can go ahead and plug in 0. So I get 2x. Right? So we've figured out that the derivative of x squared, f prime of x, would be 2x. So same idea with number 2. We're going to follow the same thing with one added step that we'll come back to later. Right? We'll come back to this piece in a second. But for now, I'm just going to stick with my limit definition. I prefer to write it out in general, right? Just so I have some kind of sense of direction, right? I find that writing out the formula in general just helps me organize my work, figure out what I need to plug in where. So let's plug in. So limit as h approaches 0. I have the square root of x plus h minus the square root of x divided by h. And you might be wondering, what do I do with this? I bring up this problem because it's a really important tool. We've talked about rationalizing the denominator, but we don't really talk about rationalizing the numerator until we get to calculus, just because it's not helpful until we get to calculus. Well, the best way I can simplify this equation, simplify this limit, is to apply my rationalization techniques that I may have learned in Algebra 2, but do it to the derivatives, to the numerator instead. All right, so if you remember from Algebra 2, we can rationalize by multiplying something by its conjugate, so that just means keeping the same terms and changing the sign in the middle. So I've got this great looking thing, but it simplifies very nicely. We know that when we rationalize a number times its conjugate gives me a difference of squares. So this is going to give me x plus h minus x over h times that whole thing, our conjugate. Okay, so simplify a little bit more, right? Our x and negative x are going to cancel out. So I can cancel out my h's too. So my h's can cancel out, and I'm left with a limit as h approaches 0 of 1 over square root of x plus h plus the square root of x. So let me go back and explain this again. I can rationalize a numerator. This is something that we don't usually talk about until we get to calculus, but it is possible. You might have had teachers that tell you, oh, you can never rationalize the numerator. They lied. You can rationalize a numerator, and it is helpful. It's essential in calculus. So we multiply by the conjugate of the thing we're trying to rationalize, right? So that just means keep the same terms, change the sign. That's what I did here. Keep the same terms, change the sign in the middle, and I do that on both sides of the rational expression. This, of course, creates a difference of squares in the numerator, which helps me to simplify my fraction, my rational expression, difference of squares. And then I can actually simplify even further by canceling out my h's. I actually find it really helpful to not distribute here so that I actually can simplify and simplify more easily. So this is simplified as far as I can make it, so I'm going to go ahead and plug in 0 for h. I get 1 over the 2 times the square root of x. So here we've established that if the function, so if f of x is the square root of x, then the derivative of that function is 1 over 2 times the square root of x. But we had one more step, right? We wanted to know what happened to f prime when x was 9. So I'm going to go ahead and just evaluate. Remember, this is what my bar means here. Evaluate for when x equals 9. So to do that, I'm just going to plug in 9. Square root of 9 is 3. 2 times 3 is 6. So f prime of 9 is 1/6. So just one last point. If f prime exists, we say that f is differentiable. Use a different color here. F is differentiable at x. And a function is said to be differentiable everywhere if f prime is if f prime exists for all x in the domain of f. Right? So if I can take the derivative of the function and evaluate for any x value I have in my domain, this function is differentiable everywhere.